Okay, gang, welcome to atmospheric circulation. The learning continues. We're moving on to the material that'll be on the second exam. The pool's a little bit deeper in this stuff. It's a little bit tougher. Don't worry, I got plenty of pool floaties to help us all out. Alright, so let me start with this series of images to help us get a sense for what we're talking about. A volcano erupted in 1991 on an island in the Philippines, which is in the tropics, and the volcanic debris from Mount Pinatubo spread around the world and covered 42% of the globe in 60 days. If we come over here, you can look at how that debris is getting spread out. So this is an image showing you that debris is spreading out over time as it covers most of the globe, and it's impressive, right? It's atmospheric circulation that's moving that debris all throughout the globe. But what's interesting, though, is that it's confined, right? It has this border to the south and not as well defined up here to the north, but partially defined up here to the north. That's kind of interesting, right? There's something in our air that's preventing this debris from moving south of probably 30 degrees south latitude and north of 30 degrees north latitude. We're going to learn about why that's the case. What's going on in our atmosphere that prevented this debris from moving, and what's in the atmosphere that allowed it to circulate. How about that? So here's our game plan. We're going to talk about atmospheric processes, the nature of wind, the general circulation of the atmosphere, modifications of the general circulation, and localized wind systems. Specifically right now, we're talking about air pressure, density, and temperature, and mapping pressure with isobars. Okay, so here's the general breakdown on the atmosphere. You probably already know this intuitively, but in case you don't, you live down here on the surface of the Earth, and above you is a 50-mile thick column of air. You can think of it like a soup made out of air molecules, right? And that soup is thickest down here near the bottom, and it thins out towards the top. And that's because these molecules have weight to them. And gravity will act upon them, and that makes it much thicker down here and thinner above. You're going to have higher air pressure here, where you have more of the air above you, and then less air pressure up here because you have less of the air above you. So let's talk about how you measure air pressure. Right now, that 50-mile soup of air above you, it pushes in all directions. It pushes up, pushes down, what have you. But let's say it pushes on this dish. It pushes on the mercury in this dish, okay? If you had a tube going into that mercury that was a vacuum, there was no air in here, so there's no air pressure in here. That air pressure outside will shoot the mercury 30 inches up this tube. Okay, that's normal atmospheric sea level. That's also the same as saying 1,013 millibars. In this class, we're going to focus on millibars. So that 30 inches is the distance the mercury shoots up, and it's also equivalent, we just call it millibars, 1,013 millibars. Okay, that mercury that gets shot up, it's because of that 50-mile column of air above that's pushing down on this mercury that shoots it up. That's the pressure that's kind of getting exerted. It's not just down, it's getting exerted in all directions. This was discovered in the 1800s when they were mining coal in England, and when they were digging the holes into the ground and removing the coal, it would fill up with water, and so they would have to pump the water out so they could keep mining. Absolute terrible job. But they noticed that when they had the pump would remove the air from the tube, and then water would shoot up the tube. Water weighs a lot less than mercury, so that water could shoot up, I mean, sometimes 50 feet. So anyway, they were really amazed by that water shooting up the tube, and somebody recognized that it was the air pressure that was shooting the water up the tube. Okay, so let's talk about high pressure and low pressure. If you watch the Weather Channel or weather on the news or whatever, you'll hear them talk about high pressure and low pressure a lot. And here's the deal. Remember, we're talking about in millibars, 1,013 millibars. That's considered normal, which would be somewhere in here. This is 1,012 millibars. This line is an isobar. An isobar is a line of equal pressure. So anywhere you walked when this map was made, wherever you walk on this line, your atmospheric pressure is 1,012 millibars, which is more or less normal. If you come up here, if you walk this line, you're at 1,016 millibars. Your pressure's a little bit higher. Up here, it's 1,020 millibars. That's considered a high pressure. Okay, this is a high pressure. Down here, we have a low pressure at 996 millibars, right? That's quite a bit lower than 1,013, then 1,000, then 1,004. And what this map does, of these massive isobars, it gives you a sense for the distribution of pressure on the planet. But here's the deal. Here's why you have high pressure and low pressure. At high pressure, the air is hitting the surface, comes down out of the upper atmosphere, and boom, it hits the surface, and then it spreads out in all directions. And then once it spreads out, it'll head over, and eventually it'll come into a low pressure. At a low pressure, the air lifts. It lifts off the surface, goes up into the upper atmosphere, and then will fall back down again on a high pressure. So you have high pressure and low pressure. High pressure you hit, low pressure you lift. Here's a map that kind of shows you the general distribution of pressure all over the planet. You can see here we have a big band of high pressure down here around 30 degrees south latitude. We also have another high pressure up here at about 30 degrees north latitude, or in this case actually 40 degrees north latitude. There's a dominant low pressure here along this red line. This is known as the ITCZ, which is called the Intertropical Convergence Zone. And the Intertropical Convergence Zone is the most dominant low pressure on the planet. Okay? And that means more air lifts at the ITCZ than anywhere else. And then up here, these high pressures, the air is hitting, it's falling down and hitting here. And then we have air lifting down here at this subpolar low at 60 degrees south latitude. Here's some sample air pressures from around the planet. Remember, 1,013 is normal. As you get lower, if you hit about 980, that's a deep low pressure system. You're likely going to get rained on. As you go down here to the lowest that we've recorded on the planet, they're all major storms. This is a Canadian record low. This is a powerful storm in 1977. The U.S. was in a hurricane, and for the world it was a typhoon. The highest pressures we find on the planet are going to be in very cold regions. U.S. is Barrow, Alaska. Canada is Dawson-Yukon Territory. And for the Earth, it's in Siberia. The reason why cold generates high pressure is air wants to fall onto cold things because cold isn't trying to rise at all. So we fall onto cold things. You don't have to fall onto cold things, but that's where you're going to have the highest high pressure. Okay, so let's talk a little bit about how wind works. We're going to talk about the pressure gradient force, wind speed, cyclones and anticyclones. Then we'll get into the Coriolis effect, geostrophic winds, and friction. Okay, pressure gradient force. This is pretty simple. So if you have a high pressure, a bunch of air is falling down, and you have a bunch of air molecules here, and then over here we have a low pressure because air is lifting. There's hardly any air molecules over here. So the air wants to move and will move from this area of high pressure to low pressure. And it's going to flow down gradient from the high pressure to the low pressure, and we call that a pressure gradient force that drives the wind. So the wind over here at this high pressure will blow over here to this low pressure. The air comes down and hits, blows across those isobars, and then lifts at the low pressure. Pressure gradient force, winds blow from high to low. Okay, now if we look at those isobars, if those isobars are spread out, that means we have a really shallow gradient, a shallow pressure gradient. There isn't that big a difference in pressure over this area, so the winds are going to be really light. But over here, where the isobars are close together, there's a big change in pressure that really drives the wind. The winds are really strong in these areas where the isobars are packed in tight. Okay, now we're going to shake things up a little bit. It would be nice if we were done and we could just say the winds blow from high to low and they blow in a straight line. The trick is they don't blow in a straight line. And the reason they don't is because we live on a planet that is spinning. And it's spinning as it goes around the sun. Okay? And so that's going to throw in something called the Coriolis effect. I'm not going to go into details yet, but that's why these red arrows are kind of going in a circle around this high pressure and going in the opposite direction around this low pressure. But the general idea is, on this map, we have a steep pressure gradient here. The winds are going to blow from high into this low, but they just don't do it in a straight line. Out here, they're going to have lighter winds because the isobars are spread out. Okay, I would diagram this in your notes. This is a simple idea. A cyclone is an area of low pressure. That means the same thing, and it means converging air. The air converges on this spot and then lifts, and you tend to get rain and storms, and you make a cyclone. An anticyclone is where the air descends. It's going to be clear skies. You'll form high pressure, and it's diverging air. Air is spreading out at that location. I'm just trying to give you time to jot that down. I guess you can just stop the video, huh? I'll move on. Okay, Coriolis effect. This will bend your brain. Oh, sorry. Gosh, wow, that was quite the stretch. Okay, so here's the deal. You live on a planet that is spinning. And it turns out, as a planet spins, the fastest place on the planet, as a result of this spin, is going to be down here at the equator. If you took a ball and you spun it, you would see that the area, like the equator, that's spinning is moving a lot faster than it is at the top of where that spin is. Right? As the planet spins, the pole's just kind of turning around in a circle, whereas the equator is going, it's whipping around. And as such, the equator is going 1,041 miles per hour. Mid-latitudes, you're going 900. Here, you're going 521. And again, at the North Pole, you're just spinning around in a circle. So that differences in speed, it's known as differences in angular momentum. Okay, and that will cause the winds to deflect. And the net result is, if you live in the northern hemisphere, the wind that wants to go straight, it wants to blow from high to low, will get deflected to the right. It always gets deflected to the right. Deflected to the right. Deflected to the right. Okay? If you were going to launch a rocket from the equator up here to the North Pole, as it takes off, right, it's heading towards the North Pole, but remember, the North Pole's not moving. It's just spinning in a circle. And this guy was hauling, so it goes, and it'll miss, and it missed to the right of its target. Okay? So, and in the southern hemisphere, it's just the opposite. The winds deflect to the left. All the winds deflect to the left. Doesn't matter which direction they're going, the winds always deflect to the left. That is our Coriolis effect. Okay, that leads us into geostrophic winds. I would write in your notes, geostrophic winds are upper atmosphere winds. They do not happen at the surface of the Earth. They happen in the upper atmosphere, and they are trippy. Okay? What I want you to imagine is you go, I see my first one was at a science center. You see them sometimes in grocery stores, but those things like where you drop a quarter on them and the quarter goes that kind of a thing. Okay, they're actually fascinating. I love those things. Geostrophic winds are like that. And the wind is your quarter, and as it goes around, it will spin in a circle. So right now, these winds are spinning around, and imagine these isobars are like the tub that you're having that circle spin around on. So they're just spinning around, and they're not really going down into the hole. That's what these geostrophic winds are doing. When they're flowing, they parallel the isobars. They're flowing along them. They're not crossing them. Remember, the wind wants to blow from high to low. But because of the Coriolis effect, it gets kicked off to the right, and it ends up paralleling the isobars. And oftentimes, the winds never really end up where they're going. It would be like that quarter that never made it into the hole at the bottom. So, hope that makes sense. They parallel the isobars, they whip around the planet, and they're cool. But they don't happen where we live. This is in the upper atmosphere. And it's combining our pressure gradient and Coriolis effect. Okay. Now we have the effect of surface friction. As you get down on the surface, out of the upper atmosphere, the wind's going to start to drag on the surface. It'll hit trees and buildings and that sort of thing, and that's going to slow the wind down. As you slow the wind with friction, you get this. Stop the video and draw this in your notes, okay? Because this is what we get. This is for the northern hemisphere. But what happens is the wind wants to blow from high to low. In the upper atmosphere, the wind would come out and then it would just parallel the isobars. Okay? But because of the surface, because that slows the wind down, the wind does cross the isobars. It will bend, right? It deflects because of the Coriolis effect. It just doesn't deflect as much as geostrophic winds, and so we spin. And for high pressure in the northern hemisphere, we have a clockwise flow. Remember, it's divergent, it spreads out, it's anticyclonic. And then as these winds go into the low pressure, remember the wind wants to go into the low pressure, and then it gets kicked off to the right. Wants to go into the low, kicked off to the right. Wants to go into the low, kicked off to the right. And so it spins in the opposite direction. It spins counterclockwise, cyclonic, convergent flow. This is what high pressures look like. This is what low pressures look like. It combines the pressure gradient force. We're blowing from high to low. It combines the Coriolis effect. We deflect to the right. Then we deflect to the right as we head in. And the friction force. Remember, with friction, instead of just spinning in a circle in both locations, we actually cross the isobars and we spin outward in the high and we spin inward into the low. And those are lame, so we're not going to worry about the movies. Okay, so here's some other diagrams that might help you with this as we kind of convert, as we talked about them. You need to understand them, right? This is, we blow from high to low, convergent, divergent. This is your geostrophic winds. We're paralleling the isobars. And then here we're down at the surface. We're adding in the friction force. Extends up to about 1,600 feet. And we get what we had in that previous slide. Okay. Now we need to talk about Hadley cells, the components of general circulation, and we might not cover Rossby waves. We'll see. Okay. I would diagram this thing. This is a Hadley cell. So this exists, this is the equator. This is 30 degrees north. This is 30 degrees south. So this is across the whole planet. We're kind of looking along the edge of the planet. Remember, this down here at the equator, we have the ITC, they forgot the Z, Intertropical Convergence Zone. This is where air lifts. Okay, it's the most dominant lifting on the planet. The reason why is this gets more energy from the sun than anywhere else, heats up the air, and it lifts, and you generate clouds and storms. It's very rainy along the equator. That's where most of your rainforests are. In the upper atmosphere, those winds, they're heading out, and they're trying to go to the poles, because that's the dominant high pressure on the planet. But so much air is heading north and so much is heading south that a lot of it deflects downward early, and it deflects at 30 degrees north and 30 degrees south over here, forming your subtropical highs. Subtropical high here and a subtropical high over here. Then down here on the surface of the Earth, you have winds that are blowing from the high pressure over here to the low pressure, right? They're blowing from high to low. In the southern hemisphere, they deflect to the left. In the northern hemisphere, they deflect to the right. And what you end up with are these dominant cells of spinning air north and south of the equator. And at the surface, you get these dominant winds, the trade winds. They're called the trade winds because back when everything was powered by sail on boats, the boats were always trying to get in these zones to be able to get from point A to point B. Otherwise, if you're over here in the subtropical highs, you're in the dead zones called the doldrums. And if there's no wind, your boats aren't going anywhere. So you're always wanting to be in the trade winds. This is our Hadley cell. The Hadley cell is the most dominant wind pattern on the planet. Cool. All right. How about this for scary and intimidating? You're going to need to know this diagram for our second exam. Don't freak out. I will show you how to make this diagram in lab. It's actually pretty easy, and once you learn how to do it, it actually looks really cool. So I'll leave that for now, but you will need to know it for the exam. Okay, so here's in cross-section. Right here we have our Hadley cell doing its thing. Some of that air will make it to the poles, and it drops onto the pole. The pole's the dominant high pressure. But right in here we have something interesting. Right here, this high, subtropical high, we send winds to the north. Okay? And when those winds hit this dome of cold air, you can imagine it like a big snowplow, hits that dome of cold air, that air is forced to rise up and over it. And that will form a dominant low pressure on our planet called the subpolar low. And that forms all our dominant pressures. We have the polar high, subpolar low, subtropical high, and the intertropical convergent zone, ITCZ, right here. Okay. All right. Jet streams. Jet streams are going to form at the boundaries of these, where you have these high pressures and low pressures. So at the subtropical highs, you have a jet stream, and then at the subpolar lows, we have a jet stream. The reason why are these are your upper level winds, these geostrophic winds that don't cross the isobars, and they whip around the planet. And they're going to form along the boundary of large warm and cold air masses. This air tends to be warmer than this air. This air tends to be warmer than this air. They can go super fast, 50 to 300 miles per hour, and they're cool. Okay. I forgot I left this slide in here with all this text. Okay, so there's a ton of text here. You can maybe pause it and then read this on your own. But here's the idea why you have a jet stream. Okay, this air here is warm. The air here is cold. Where the cold air is, the air is denser, right? It's cold. Most of the air molecules are down near the surface. Over here, it's light, it's fluffy, it's warm. There's not as many air molecules near the surface. But as you get into the upper atmosphere above the warm air, you have a fair number of molecules because they're warm and they're not rising, but there's warm air up aloft. But in the cold air, there's hardly any cold air aloft. And so what you have is a bunch of molecules over here where it's warm in the upper atmosphere, hardly any over here where it's cold, and they try to blow from the hot air into the cold air. But because of geostrophic winds, as they go there, they get deflected to the right, and they whip around along the boundary of this warm and cold air, forming our jet stream. How cool is that? Rossby waves. First, they're named Rossby waves. How can you not love something named a Rossby wave? But a Rossby wave is this boundary between the cold and warm air. It's going to shift. Okay, it's going to move. Sometimes it's roughly circular, but other times it gets all amoeba looking and it spreads out. The reason why that's relevant is later on we're going to learn about cold fronts and warm fronts. Again, don't worry about the movie. And these Rossby waves, as they get really developed, they're going to start forming these cold and warm fronts that become important when we learn about storm systems. Okay, so I'm going to review some stuff with you right now. At the equator, ITCZ, most dominant low pressure on the planet. Get more energy than anywhere else. Air's lifting like crazy. Okay, it heads out. A lot of it's heading towards the poles, and we'll make it there. But a lot of it gets deflected down early, forming your subtropical highs right here. Okay, boom, falls down, subtropical highs here. And then the winds want to blow back from high to low, and again from high to low. These are your trade winds. Deflects to the right in the northern hemisphere, to the left in the southern hemisphere. Okay, as you head south of the southern subtropical high, you're going to deflect to the left, and you're going to run into this dome of cold air, forming our subpolar low down here at this region, and it'll form another subpolar low up here as well. And then at the top of the planet, we have our poles. Oh, I forgot to mention these winds here, and I'm going to cover this when we do it in class. These winds are called the westerlies. These winds are called the northeast trade winds. These winds are called the southeast trade winds. These ones are called the westerlies. And these are called the north... what is it? Give me a second. Right. The northeast trade, or the polar easterlies. These are called the easterlies. The polar easterlies. Out here at both poles. I'm going to reinforce the names of the winds when we talk about it in class. Okay, so this is just sort of an early snapshot. Okay, now let's talk about some modifications to the general circulation. So on that last slide, I showed you, boom, this is how the atmosphere looks, but the reality is the atmosphere will shift. So in the summertime, the ITCZ will move northward. Comes way up here, sometimes as north as 25 degrees north latitude. And in the winter time, or at least in our winter, it's going to move south. Okay, because the sun's dominant down here, and then the sun's dominant up here, and then the sun's dominant down here. So all these pressure systems move up and down. Okay. What's interesting about that is that generates what's known as the Asian monsoon. In the summertime, the ITCZ, the most dominant low pressure on the planet, sits right along India and Southeast Asia, and you have a bunch of the trade winds right here that are blowing in to that ITCZ, and it's coming off the warm Indian Ocean and Pacific Ocean. So you have a source of warm, moist air, boom, hits that low pressure, lifts. You're going to generate tons and tons of rainfall. And here's your look at what the rainfall looks like for the months of June, July, August, and September. Okay, the monsoon months, dumping rain. But in the wintertime, boom, that ITCZ moves way far to the south as the sun is more over the southern hemisphere. Then this is the most dominant low. You have a dominant high pressure over the cold Asian continent. That's blowing cold, dry air across India and Southeast Asia to the ITCZ, and it dries out the whole region, and they get hardly any rain. Okay, so the movement of these pressure belts obviously has a huge impact on weather on the planet and generates the Asian monsoon. Here's more localized conditions that generate or that result into kind of cool pressure systems. You can get sea breezes and land breezes. So you might have felt this if you've been to San Diego or Los Angeles. You go out there and you're on the beach and you want to fly your kite. You're always going to have a good wind coming off the ocean onto land. It's called the onshore breeze or sea breeze, and it feels fantastic because usually it's hot outside. If you go inland, it's much hotter. That sea breeze that you're feeling coming off the ocean is over the cold ocean. We end up with a high pressure, right? It's easy for air to fall onto something that's cold. You generate a high pressure. Out over here, we get a low pressure. That's because the land heats up a lot more than the ocean does during the day. That low pressure causes air to lift, and we get this circulation of air that at the surface moves the cold air on the ocean onto the land, making it really nice. And this warmer air over the land moves out over to the ocean in the upper atmosphere. At night, it reverses. At night, the land cools off much quicker than the ocean. So air over the ocean will rise, and you're going to get a wind that blows from the land into the ocean, known as an offshore breeze or land breeze. And so this is where, if you were out here on a boat, you could smell pine needles and other stuff coming from the land as that breeze blows offshore. Kind of cool. And that's it. So here's your things to know for this lecture. Define and describe air pressure, world wind patterns, including the Hadley cells, westerlies, trade winds, etc. Diagram. I'm going to explain the diagram in detail for you in lab. Driving forces in the atmosphere, including pressure gradient, Coriolis, and friction. I need you to know what a geostrophic wind is and where you find them, the difference between cyclones and anticyclones, jet streams and Rossby waves. I need you to know both of those. Remember, jet streams form at the boundary of cold and warm air masses. The winds whip around the planet, never making it to the low pressure. Rossby waves are that contact between the warm and cold air shifts over time, gets very amoeba-like. Local wind, sea breeze, land breeze, and I need you to understand how you can get seasonal variations of our pressure systems and how that generates the Asian monsoon. Hope you guys liked it. Have a great day.